Hi everyone, this is Lee here. In this video, we are going to go over potential energy. Alright, let's begin. So in the other video, we looked at kinetic energy, and kinetic energy was the energy of moving objects. So what is potential energy? The energy of not moving objects? Well, sort of. So there's multiple forms of potential energy. One of them is gravitational potential energy. And that's what we're going to be looking at mostly. And the other one is what we call spring potential energy. Okay, so there's gravitational potential energy and there is spring potential energy. Now, potential energy for any object is just like the word implies. It's how much it can do, how much energy it has stored inside, or how much energy that, if the correct things were to happen, like the potential energy would lead to some form of energy. And usually for us, that'll be kinetic energy. So the two are very closely linked, potential energy and kinetic energy. So the best way to approach it is just to take a look at a couple of scenarios. Now, we're going to focus on the gravitational potential energy first. A lot of times you might see potential energy written as PE, but I haven't seen that in a long time. In fact, I haven't seen that since, I think, like high school. And so the way that I've always seen it, especially in college, is uppercase U. Okay, uppercase U, not lowercase u, but uppercase U. And that is potential. Now, if it's gravitational potential, we're going to put a little tiny little subscript G next to it. Okay, to designate that as gravitational potential energy. And so, like, with the same train of thought, spring potential energy is a capital U with a tiny little subscript S. Okay, so that tells me that is a spring potential, and this is gravitational potential. Okay, so with gravitational potential energy, the formula comes with three variables. M for the mass, so the object, the acceleration due to gravity, G, and H, the height above the Earth, basically. Okay, so if you remember from the last video, we discussed that work and energy are very closely related. In fact, work is the change in energy. Once again, I'm gonna highlight this. This is one of the key concepts of our universe. Very important. And so with this idea, we can actually see how this equation came about. So let's say we had a box, right? Let me draw a straighter line. Let's say we have a box. All right, so we have a box and we lift it. We lift it to a height of h. Oh, you see, we already have h there. All right, so we have this box and it is, let's say there's a ledge there. All right, so we have a box on a ledge. It's up there. Now, let's say we have a cat. Meow. All right, so we have a cat, and this cat is going to do cat things. And one of my favorite things to do is watch videos of cats when they get close to an object, and they just kind of tap, 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 right, and they swat it off. Okay, so when the cat swats off the box, like ever so slightly, the box, even if it doesn't like fly off, it kind of tilt off, right, and then the box will go pew, and it'll crash into the floor. Now, that motion right there is very important because when the box is moving, crashing into the floor, that is kinetic energy, right? Because it's the energy of motion. So you might be thinking to yourself, well, if it's moving and it's called kinetic energy, where did the energy come from? And that's the big idea behind potential energy. Potential energy answers for us, where does this energy come from? And in our case here, it will be the kinetic energy. And the answer to that is, well, it came from potential energy. The reason why this object was able to move was because it had potential energy. I'll say that again. The reason why this object was able to move, kinetic energy, was because it had kinetic energy, potential energy. All right, so the box is on the floor, and you're like, darn you, kitty! Right? You knocked over my styrofoam box. I don't know why you have a styrofoam box, but and so you lift this object back up onto the shelf, right? And then you look at your cat and you say, kitty, don't do that again. If you know anything about cats, they won't listen. And so see, look at that motion right there. Not the whole scolding of the cat, but when you lifted up that styrofoam box up onto that ledge. When you lifted the box, ooh, force, up onto the ledge, ooh, displacement. What did you just do? That's right. You just did work. So you did work on the box and you put it on top of the ledge. Now, if you remember, we said that work is a change in energy. So you just did work on the object. Now we know this because when the object is on the floor, okay, it's not moving, but when you exerted a force on it and you moved it, you did work. And that work came in the form of kinetic energy. So while you're lifting up the box had kinetic energy because it's moving. But then you put it on top of the box, okay, and now the box is no longer moving. But we just did work on it. So where is the energy, right? Because we know that work is a change in energy, and you just did work. Like, was there only energy while it was moving? And the answer is no. Because you lifted up the box and you put it on top of the shelf. Now the box has energy that you did work on that box, so you stored energy within that box, right? The box now has potential energy. Now, the physics behind it gets a little bit deeper, right? Like we say the energy is actually stored in the field. Ooh, this mysterious idea of the field. But that's for a later time and date. But the important thing is now that the box is on top of the shelf, it now has potential energy. How do we know it has potential energy? Well, if the cat comes by, meow, right, and then taps the styrofoam box again, it will now be able to fall. And that's kinetic energy. All right? Okay, so simply put, if we take a look at this equation here, we know that if we put the styrofoam box M on top of this shelf, right, it has to go a height h, it has potential energy. And the reason why we put the acceleration due to gravity there is, think about it, if we were in an environment where there was no acceleration due to gravity, okay, where there were no forces of gravity involved, and the cat were to tap that styrofoam box, would it fall? And the answer is no. And so the potential energy can only exist if we have this gravitational constant, this acceleration due to gravity g. And for us here on Earth, that's 9.8, but sometimes we might use 10. Okay, now if you remember, so we're going to go back to that little thing I said we want to go into. But if you remember when I said, well, where is the energy stored? Okay, and I said, well, technically it's stored in the field. Right, that's right there. That's the G. It's stored in the gravitational field. Really cool stuff. Okay. And so here we can come up with our next equation. We say that work is equal to the change in energy. Okay. And in this scope, we can say that the work is equal to the change in the gravitational potential energy. Right there. Okay. And simply put, is just mgh. Because the h is like the change in height, and so that takes care of the delta. Boom. Equation. Okay, so if we were to take a look at the relationships, right, between U, G, M, G, and H, right, we're taking a look at relationships. And if you remember, when we take a look at relationships, we don't care about the constants. We don't want to know about the constants. All right, so U, G equals MH, and we can say that the potential energy and the mass, okay, because it's on opposite sides of the equal sign, and it also has a one-to-one relationship, it is directly proportional. Okay, potential energy, gravitational potential energy and height, right, that is also directly proportional. And so let's take a look at this. So what this means is if something has more mass and you raise it to like a height, it'll have more gravitational potential energy. And for this h, this height, that just simply means if you raise the object up higher, it'll have more gravitational potential energy. And that kind of makes sense, right? So if we remember that the gravitational potential energy leads into kinetic energy, the higher something is upwards, and as it's falling, it'll fall faster and faster and faster. So it has more and more and more energy, kinetic energy and gravitational potential energy. And for this m here, the more massive something is, the more energy, right? It takes more force to lift up that object. And if it takes more force, it takes more work. More work means more energy, right? Cool. Yeah, and so we have this proportion. The other thing that we can take a look at is M and H. And because they're on the same side of the equal sign, and we could also move M on the other side so that it'll be in the denominator. I go over that in the other energy video. We say that this is inversely proportional. Okay? All right, cool. Here are my three relationships right there. All right. Next, let's take a look at spring potential energy. Spring potential energy. All right, so the equation for spring potential energy is 1/2 lowercase k x squared. Okay, now let's go over the variables here. So we can say that the spring potential energy, right, that's just spring potential, right? So this is the potential energy. 1/2 is just a constant, and this K, that's what's important here. This is what we call the spring constant. The spring constant. And basically that tells us how stiff a spring is. Like if it's like super springy, right? It has a high K constant versus like something that is not springy at all. That has a low spring constant, and that's a very important idea. So for example, your cars have like these shock absorbers that has a super high spring constant because your car is bouncing around a lot, and we don't want all that vibration to go into your body and make you sick, like car sick. So the shocks in your cars, they have a high spring constant compared to something that's like not, springy at all. Like let's say a Slinky, right? If you had a Slinky and you were to replace the shocks in your car with the Slinky, it's not going to get the job done. So the Slinky can be said to have a low spring constant. So this is just describing the spring itself, how springy something is. And X here is it's the displacement. Okay, it's the displacement of the spring, or the how much it's stretched. Okay, how much it's stretched, and it's how much it's stretched from its natural resting position. So this is the best way to approach it is to have a sketch for this one. All right. So if I have, let's say like a pen cap. So if we have a pen, I was gonna say a pinball machine, but I don't think everyone knows what a pinball machine is, but we can do a pinball machine. All right. So we have a pen there, and if you click it, right? So every time you click it, if you've ever taken a pen apart, whenever you click it, there's actually a spring inside there that you're pushing down. So when the spring is not pushed, so we'll do like a blown up version of the spring. Okay, so when the spring is not pushed, it's, let's say that's a displacement of 0, right? But when you push down the spring, so let's say we scrunch up the spring, the displacement would be from this height down to here. Right? So that's our displacement. That's how much you push down the spring. Now, when you push down on the spring, what's it gonna do? It's gonna boing, right? It's gonna spring away, and that action right there, that boing, right? That spring away, that is our evidence that there is potential energy. So whenever you push down on the spring, you are doing what work? Yes, you are doing work on the spring. So whenever you do work on the spring, you are giving it some of your energy, right? And so in this case, we say that there is spring energy that you are storing. So when you do work on the spring stores it as energy, and we know that because if you were to let it go, it'll spring away. I like how I'm using the word spring a lot here. Okay, so that springing away, like if you were to attach, let's say, we're gonna go back to pinball, right? So if we have a pinball right there, so this is my pinball. Okay, and we push the pinball down, or like this could be like anything, like I know McDonald's had a lot of these toys where you kind of just like scrunch down something and you let it go and like pops away. They're called poppers, right? Okay, so if you push down on the object and you let it go, that spring potential energy that leads into some kinetic energy. So we know that whenever you push down on an object, when you release it, all that spring potential energy, it turns into kinetic energy. Okay, so that's spring potential energy, and sometimes you'll come across this in our problems, but it's it's important for us. And we will go into springs a little bit more later, and this equation will show up. But for your record, that is the spring potential energy, and it is the energy stored in springs. So let's take a look at the equation itself so that we can take a look at the relationships. So we have the spring potential, and we have, let's say, K. Okay, so what this means is, well, first of all, it's directly proportional. Okay, it's directly proportional. And we know that because it's on opposite sides, and that 1/2 is just a constant. Now, this is determining how springy something is. So let's say we have something that is super duper, super springy, like super bouncy. It'll have more potential energy, right? So it's able to launch things at a faster rate, kinetic energy, right? So the two go hand in hand. Versus something that is like not so springy, it's not going to hold much energy. And the other one is the displacement. Okay, so here, remember our little trick? We know that it is squared, but we're only looking at the displacement, the positioning of the spring itself. And this is a square relationship. And we know it's squared because within the equation, the x is squared. So what this means is that the more and more you push down on a spring, right, the more you push down into it, it's actually storing a exponential amount of energy. So like if you sort of kind of push down on the spring, not much energy, versus if you push a little bit more, the amount of energy it stores, it increases by a lot, okay, in a squared amount. And so that's what that means there. And the spring and the displacement squared, this is a directly proportional relationship, and just the same idea, right? The more you push down on a spring, the more energy can store. Now I'm saying that you're pushing down on the spring, but you can also pull on a spring, right? And the x, or the x squared, that's the same thing. It's just how far away it is from its resting position. All right, and the last one that we want to take a look at is the k, right? The spring constant, and the, let's say, the displacement squared. Because it's on the same side, we can say that this is inversely proportional. Now, what this means is, this is actually very important, so we'll take a little bit of time going over this. If something is more and more springy, okay, the x squared will decrease, right? So if k increases and our x squared decreases, that's the inversely proportional. So what this means is, remember what we're keeping constant. We're keeping the spring potential energy constant. So what this means is that if you have something that is super springy, right, super resistant to moving, you only have to push down just a little bit in order to store energy, a lot of energy, versus the other way, right, the inverse, so down and up. Get rid of the other ones. So if you have something that's not very springy, you have to push on it a lot in order to store up that energy. So that's what that means. And of course, the last one is this one here, and this is the inverse square proportion. Right? Okay. Cool. Well, this was a video on the potential energy. We learned about gravitational potential energy and spring potential energy. Now, these are just two types of mechanical energy. There's other types of potential energy, like the potential energy, let's say, in foods, right? Whenever you eat, you gain some of that potential energy so that you are able to move and do things. But what we're going to focus on is the mechanical energy, and mechanical energy will be just the kinetic energy, the gravitational energy, and spring potential energy. We went over the two equations for those potential energy. We linked how work is related to energy with our cat, that darn cat. We looked at the proportions for both of the equations. In the next video, we're going to go over the conservation of energy. I'll see you next time. Bye-bye.